Jnanam paramam dheyam. Knowledge is supreme.
Then let us look at the mass transport between bubble and cloud. So, suppose if the so let us first look at the transport of the reactant from the bubble to the cloud. So, the suppose if A is the reactant, so the flux at which the species A is being transported from the bubble to the cloud, flux at which it is transported is actually given by the mass transport coefficient KBC multiplied by CAB minus CAC, where CAB is basically the concentration. So, that is the concentration of the species in the bubble phase, and this is the concentration in the cloud phase. So, this expression provides the flux at which the species is being transported from the bubble phase to the cloud phase. And similarly, the for transport from the cloud phase to the emulsion phase, the expression can be written as KCB, where KCB is the corresponding mass transport coefficient, and the previous case the KBC is the corresponding mass transport coefficient multiplied by CAC minus CAC, where CAC is the concentration of species A. So, CAC in the cloud phase, and this is the concentration of species in the emulsion phase. So, this is for the mass transport between the cloud phase and the emulsion phase. So, similarly, one can actually write a similar transport for the product species which is being transported back from the emulsion phase back into the cloud phase and back into the bubble phase. So, Cooney-Levenspiel, once again they have developed a correlation in order to find out what these mass transport coefficients are. So, they have developed a correlation for estimating these mass transport coefficient, and so that is given by KBC, which is the mass transport coefficient for reactant species to go from the bubble phase into the cloud phase, and that is given by 4.5 multiplied by the minimum fluidization velocity UMF divided by the diameter of the bubble plus 5.85 into the diffusivity DAB to the power of 1 by 2 into gravity to the power of 1 by 4 divided by the diameter of the bubble to the power of 5 by 4. So, that is the correlation which provides an estimate of what is the mass transport coefficient between the bubble phase and the cloud phase. Now, because the mass transport actually occurs by the exchange of volume between the cloud phase and the bubble phase, one could assume that the mass transport between the mass transport coefficient for transport from the bubble to the cloud phase should be approximately equal to the mass transport coefficient from the cloud phase back into the bubble phase. And typically the order of magnitude of this mass transport coefficient is of order of 2 second minus 1. Remember that KCB is a mass transport coefficient. So, now let us look at the correlations for cloud to emulsion, mass transport from cloud to the emulsion, and that is typically given by KCE equal to KEC. That is, the KCE is the mass transport coefficient for transport from the cloud phase to the emulsion phase, and KEC is the transport of products, let us say, from the emulsion phase back into the cloud phase. And so, that is given by the correlation 6.77 into epsilon mf, which is the porosity at the minimum fluidization velocity, multiplied by the diffusivity dAB into the velocity of the rising bubble divided by the diameter of the bubble to the power of 3, cube of that to the power of 1 by 2, square root of the whole expression, and this is typically of the order of 1 second minus 1. So, that is the order of magnitude of the mass transport coefficient. So, let us next look at the reaction in the fixed fluidized bed reactor. Remember, there are three factors which are controlling. One is the mass transport of the reactant species from the bubble phase into the cloud and into the emulsion in order for it to get in contact with the catalytic particles. And then the next step is the reaction which is actually occurring inside the catalytic sites to form the product, catalytic reaction which is happening inside the catalyst site to form the products, and once the products are formed, they are transported back into the bubble phase. So, let us look at the reaction in the fluidized bed reactor. Let us look at the reaction. So, suppose if it is an nth order reaction, then the reaction rate in the bubble phase can actually be given as Kb into Cab to the power of n. So, that is in the bubble phase, and similarly for the cloud phase it can be given as Kc into Cac to the power of n, where Kb and Kc are the corresponding rate constants, and then for the emulsion phase it can be written as Ke into Cae to the power of n, where the Cab is the concentration of the species in the bubble phase, and Cac is the concentration of the species in the cloud phase, and Cae is the concentration of species in the emulsion phase. Now, it is important to write these rate expressions in all three phases. Although the emulsion phase actually contains the maximum number of particles, the bubble phase and the cloud phase also will have some particles, and therefore, it is important to write these expressions because the reaction can in principle occur in the catalyst particles in each of these phases. So, now next we can write a mole balance. Once we know the reaction rates, we can now write a mole balance in the fluidized bed reactor in order to capture the behavior of the concentration of the reactant species in the reactor. So, now let us consider a small element Let us consider a fluidized bed reactor, and if let us say that the fluid is entering at a superficial velocity of u naught, and then there is a small element between z and z plus delta z, and if you assume that the upward motion or the direction of the fluid flow is the positive direction, then we can now write a mole balance for the bubble phase. We can now write a mole balance for the bubble phase, which is basically rate due to flow into the bubble phase minus the rate with which the fluid stream leaves because of flow, plus the rate at which the fluid species is actually leaving the bubble phase because of mass transport, plus whatever is being generated, that should be equal to 0 under a steady state condition. So, if you assume it steady state conditions, then this is the mole balance. So, now when we plug in all the corresponding expressions, rate due to flow that is into the bubble phase is given by the velocity of the bubble ub multiplied by the corresponding cross section AC into concentration of the species in the bubble phase multiplied by delta. So, delta is basically the fraction of the bed that is actually in the bubble phase, and that at that particular location z, that is the rate at which the species is entering this small element in the bubble phase, and then the rate at which the species is leaving in the bubble phase at z plus delta z is given by ub AC Cab into delta at z plus delta z, and the mass transport is given by minus k Bc into CAB, that is the concentration of the species in the bubble phase, minus the concentration of species in the cloud phase, multiplied by cross section area into delta Z. So, that is the rate at which the species is actually leaving the bubble phase and going into the cloud phase, minus the corresponding reaction rate. So, that is KB, if that KB is the reaction rate constant, into CAB to the power of n. So, that is the CAB is the concentration of species in the bubble phase multiplied by the cross section into delta Z into delta. So, that should be equal to 0. So, that is the mole balance for the species in the bubble phase. So, now we can rewrite this mole balance as by taking a limit that. So, by taking limit that delta Z goes to 0, we can rewrite this model as UB, which is the velocity with which the bubble is rising inside the fluidized bed reactor, into dCAB by dZ. That should be equal to minus KB CAB to the power of n minus KBC, which is the mass transport coefficient between the bubble and the cloud phase, multiplied by CAB minus CAC. So, that is the mole balance for the bubble phase. So, similarly for the cloud phase, the mole balance is given by UB into delta into 3 times UMF. A very similar balance can be written, and taking the limits of delta Z going to 0, one would get that the expression for mole balance for the concentration of the species in the cloud phase is basically given by this expression here. Into dCAC by dZ, that should be equal to the mass transport coefficient of the species from the bubble to the cloud phase, that is basically added into the cloud phase, multiplied by CAB minus CAC minus KCE, that is the mass transport coefficient for transport of the species from the cloud phase into the emulsion phase, that is given by CAC minus CAE minus Kc, which is the rate constant for the reaction if the catalytic reaction is happening in the catalyst particles which may be present in the cloud phase. So, that is the mole balance for the cloud phase, and then the mole balance for the emulsion phase is given by, for the emulsion phase, that's given by UE, which is the velocity with which the emulsion phase is moving, into 1 minus delta minus alpha into delta divided by delta into dCAE by dZ. That should be equal to the mass transport coefficient between the cloud and the emulsion phase into CAC minus CAE minus the rate at which the species is actually being consumed because of the reaction that may be happening in the emulsion phase. So, if we need to find out what is the concentration of the species in the bubble phase, in the cloud phase and the emulsion phase, then these 3 equations have to be solved simultaneously. So, these things have to be solved simultaneously. So, once we solve them simultaneously, then we can find out the expression for CAB, CAC and CAE, what is its relationship, how the profile changes with respect to the position inside the fluidized bed reactor. As this is a nonlinear equation, it cannot be solved analytically, and one has to resort to numerical techniques to solve these set of equations. However, if we make an assumption that the reaction is a first order reaction, suppose if we assume that it is a first order reaction, suppose if the reaction, the catalytic reaction which is happening is a first order reaction, then we can actually write the expression as UB into dCAB by dZ, that is equal to minus KB into CAB to the power of n minus the mass transport coefficient KBC into n equal to 1 CAB minus CAC, and the other, suppose if we assume that that dCAC by dz, which is the rate of change of the concentration with respect to position in the cloud phase, if this is very small. And similarly, if we assume that dCAE by dz is also very small, then we can write the model equations for these two concentrations as they basically become like this, where the mass 0 equal to the mass transport coefficient KBC multiplied by CAB minus CAC minus KCE into CAC minus CAE minus Kc into Cac. And similarly, for the emulsion phase, the mole balance will become Kce into Cac minus Cae minus Ke into Cae. So, that is the mole balance for the emulsion phase. Now, because it is a catalytic reaction, so Kb, which is the corresponding rate constant, suppose Kb, Kc and Ke, these are the corresponding rate constants for the reaction which is actually occurring in the bubble phase, cloud phase and the emulsion phase respectively. So, now suppose if it is a catalytic reaction, and if gamma B is basically the ratio of volume of solid catalyst in the bubble phase divided by the volume of the bubble. So, this provides an estimate of what fraction of the bubble volume is actually contained by the solid particles which are actually carried by the bubble phase. So, if we know this expression, then we can actually rewrite the rate constant in terms of the intrinsic rates. So, that will be equal to Kb is given by gamma B, which is the fraction of the volume which inside the bubble, which is which is occupied by the solid particles carried by the bubble, into the corresponding reaction rate which is occurring in the catalyst surface of the particles. And so, now that can actually be rewritten as gamma B into rho C into K prime, where K prime is the gram mole, that is reactor, per unit weight of the catalyst per unit time, and rho C is the corresponding density of the catalyst. So, similarly, we can actually write Kc is basically equal to gamma C, which is the volume of solid catalyst which is present, fraction of volume of the cloud phase which is occupied by the solid catalyst, that multiplied by rho C into K prime. So, and similarly Ke equal to gamma E into rho C into K prime. So, notice that the K prime is basically same because it is the same catalytic reaction which is happening in the solid particles which are present in these three phases. The overall reaction rate is different in these three phases because the amount of catalyst particles which is present in each of these phases are different, and therefore, that is actually accounted for in the overall reaction rate constant. So, now we need to estimate what is this gamma B, gamma C and gamma E are. So, if we know that estimate, then the mole balance can actually be solved. So, we need to find out what is gamma B, gamma C and gamma E. So, once we know this, we can actually solve the model equation. And so, gamma B is essentially given by 3 into UMF by epsilon MF divided by UB minus UMF by epsilon MF, and similarly gamma E is given by 1 minus epsilon MF into 1 minus delta by delta minus gamma C minus gamma B. So, that is gamma E is the fractional volume in the emulsion phase which is occupied by the solid catalyst, and gamma B is the corresponding fractional volume in the bubble phase, and gamma C is the fractional volume in the cloud phase occupied by the solid particles, which will be 1 minus epsilon MF into MF by epsilon MF divided by UBR minus UMF by epsilon MF plus alpha. So, these things can be estimated simply by estimating in terms of the properties such as the porosity and the minimum fluidization velocity, etc., what is the volume of the bubble and what is the fraction of the bubble which contains the solid particles, what is that volume. So, once we estimate these volume and take the ratio, we can find out these expressions for the volume fractions in each of these respective phases that is contained by the solid particles. So, now if we know all these expressions, then we can now solve the model equations in order to find out the design parameters of the fluidized bed reactor. So, the complete mole balance for the first order reaction is basically the set of mole balance equations are, suppose if we assume that the time is equal to Z by UB. So, remember that the time that is spent by the bubble inside the bed is actually an important parameter that controls the performance of the fluidized bed reactor. So, T here refers to the time that is actually spent by the bubble inside the fluidized bed reactor till this position Z. So, UB, where UB is basically the velocity with which the bubbles are actually rising inside the fluidized bed reactor. So, the mole balance will be dCA B by dt, that is equal to minus gamma B into the rate constant, into the specific rate constant for the catalytic reaction multiplied by CAB minus KBC into CAB minus CAC, and the second equation is KBC, which is the mass transport coefficient between the bubble and the cloud phase, that multiplied by CAB minus CAC, that should be equal to gamma C into the rate constant for the catalytic reaction into CAC plus the mass transport coefficient KCE into CAC minus CAE, and then the third equation would be KCE into CAC minus CAE, that should be equal to gamma E into the rate constant for the catalytic reaction into CAE. So, now if I look at the third equation, from third equation I can actually rearrange the third equation and find an expression for CAE, and that CAE is equal to KCE divided by gamma E into K catalyst, which is the reaction rate constant for the catalytic reaction, plus KCE into CAC. So, further rearrangement of the expressions can actually be performed in order to estimate what is the concentration of the species in the cloud, and that's from second equation we can find out. So, substituting the expression for the concentration of the species in the emulsion phase into the expression for the mole balance expression for the concentration of the species in the cloud phase, we can find out the expression for the concentration of the species in the cloud phase, and that is given by KBC into CAB divided by gamma C into K catalyst plus KCE into gamma E K catalyst divided by gamma C into K catalyst plus KCE plus KBC. So, that is the corresponding mass transport coefficient. Now, plugging in all these expressions into equation 1. So, plug in expression for CAC and CAE in equation 1, we will get. So, what we can find is that minus dCAB by dt, that is equal to K cat into CAB into some overall constant Kr, and this Kr is essentially given by the overall constant Kr is given by gamma B plus 1 divided by K catalyst by KBC plus 1 divided by gamma C plus 1 divided by 1 by gamma E plus K catalyst divided by KCE. So, that is the expression for the overall reaction rate, and if I look at this expression, gamma B is basically captures the 1 by gamma B is the resistance to reaction in the bubble and K cat by K BC is the resistance to mass transport from bubble to cloud, and gamma C is resistance to 1 by gamma C is resistance to reaction in the cloud phase, and this is the resistance to reaction in the emulsion phase, and this is the resistance to mass transport from the cloud to the emulsion phase. So, this overall constant essentially captures the resistances, that is all the resistances that are actually present inside in this system. So, now using the appropriate stoichiometry, we can say that CAB is equal to CAB 0 into 1 minus x, where CAB 0 is the concentration of the species at the inlet of the fluidized bed reactor, and so we can now rewrite the mole balance as dx by dt equal to K cat into Kr, that is the overall rate constant, which captures all the resistances which are involved, into 1 minus x. So, now we can solve this equation, and you can find that ln of 1 by 1 minus x, that is equal to K cat into Kr into T. So, this provides a relationship between the conversion as a function of the time that is actually spent by the racing bubble inside the fluidized bed reactor. So, from this we can find out what is the overall height that is required. So, that is equal to T into UB, that is the height that is required for, suppose if a specific conversion is set, what should be the conversion, supposing if for a desired conversion, if TD is the time that is required from this expression for the desired conversion. So, this corresponds to the desired conversion. If this corresponds to the time for the desired conversion, then the height of the bed can actually be estimated by using this expression Td into Ub, and that is equal to Ub divided by K cat into Kr into ln of 1 by 1 minus x. And from here we can find out what is the weight of the catalyst, that is given by rho C AC into AH into 1 minus epsilon MF into 1 minus delta. So, that is given by rho AC UB into 1 minus epsilon MF into 1 minus delta divided by K cat into Kr into ln of 1 by 1 minus x. So, that is the expression for the weight of the catalyst. So, let us quickly just rewrite the weight expression for the weight of the catalyst. So, that is given by rho AC UB into 1 minus epsilon MF into 1 minus delta divided by K cat into Kr, which captures the, which is basically reflects the overall resistance into ln of 1 by 1 minus x, and the height which is required for the bed, which is an important design parameter, is basically Ub divided by K cat into Kr into ln of 1 by 1 minus x. So, let us summarize what we have learnt in this lecture. So, what we have seen is we have actually designed a fluidized bed reactor. We started by looking at various parameters, estimating the various parameters which is required to find to design a fluidized bed reactor. For example, what is the how to estimate the velocity of the racing bubble, how to estimate what is the fraction of the bed that is actually occupied by the bubbles, etc. And then we found out what is the rate law that corresponds to the catalytic reaction that is happening in the particles, which may be present in the bubble or cloud or the emulsion phase, in any of these three phases. And then we looked at the mole balance for the species in each of these phases, which incorporated the transport of species from the bubble phase to the cloud phase and cloud phase to the emulsion. And using this mole balance, we actually assumed that it is a first order reaction and found out what are the important design parameters, such as the height of the fluidized bed and weight of the catalyst, which is required for a given conversion to be achieved using a fluidized bed reactor. Thank you.